Hey guys, what is up? What am I saying? What? What's up, people of the internet? It's Jared here with Physics Fix, and I'm here to bring you easy, practical concept breakdowns, and I'll be solving practice problems for you so you can see how these concepts actually apply. So let's get started.
All right, so today we're going to work on a problem that includes gravitational and centripetal force. So we'll start by reading it out loud. A satellite of mass m is in a circular orbit. This will become important. Circular orbit, and we'll come back to that. Is in a circular orbit about the Earth, mass equals capital M, at a height h above the Earth. The height h is equal to double the magnitude of the radius of the Earth. All right, so let's start drawing this out because we've got a lot going on here, and it's important to make sure we understand how things are playing out. So we'll say that this is the Earth, and it has a mass of big M, and we've also got the satellite, which is of mass little m. So they tell us that it's a height h above the Earth. So when they say that it's above the Earth, this is referring to it being above the Earth's surface. So that would be at this line right here. And then the question becomes, do we draw it at the center of the satellite? Do we draw it to the edge of the satellite? And honestly, I'll tell you, it doesn't really matter because the size of the satellite relative to the Earth is negligible. But I'll just draw it to the center of the satellite for right now. So they tell us that this right here, h, the satellite is h above the surface of the Earth, and we know that the radius of the Earth is equal to r. Okay, good to know. They also tell us that h is equal to double the magnitude of the radius, so h equals 2r. Okay. What velocity should the satellite have in order to maintain its orbit? Okay. So instantly in my mind, we're looking at problems that involve satellite, a planet. Whenever you have these kind of problems, they're generally involving gravitational forces, where you use your gravitational constant times the mass of one object times the mass of the other, divided by the distance between the centers of the object squared. And I'll write this in another pen here. This is center to center. So in our case, the value of r of center to center is equal to h, the center of this mass, h, to the edge of the Earth, plus the distance from the edge of the Earth to its center, which is r. Now, we drew an expression earlier where we said that h is equal to 2r. So we'll redraw that down in here and substitute that. We'll substitute h equals to 2r in for h down here, and we'll say that r, big R, is equal to 2r plus r, which equals 3r. Okay. So now what we're going to do is we're just going to draw a free body diagram on our satellite. So here's our satellite, mass m. The only force that's acting on this is a gravitational force pointing towards the center of its rotation. If this is its path, the gravitational force is pointing towards the center. So if we do a sum of forces on our satellite, sum of forces on the satellite, that equals force of gravity, and that equals mass times acceleration. Now previously, we said that the force of gravity is equal to the gravitational constant times one mass times the other mass divided by the distance between the centers of the mass squared. So I am just going to go ahead and I'm going to substitute this f of g in down here. So we will say that g times the mass of the Earth times the mass of the satellite divided by r squared equals mass of the satellite times the acceleration. So our masses cancel, and we're looking at this equation thinking, okay, we're getting closer, but we don't have velocity anywhere in here, and they're asking us for velocity. But they did tell us a key in the question earlier. They said that it is traveling in circular motion. Now that should instantly, in my mind at least, trigger a bell that that we're doing circular motion, so this is a centripetal force, and our acceleration now is equal to the velocity squared divided by the radius of the path. And if you're wondering, this r right here is equal to this r right here. All right. So we're getting back to our problem here. So let's substitute v squared divided by r in for this equation. So we have g times mass of the Earth divided by r squared equals, our m's canceled, so we have now v squared divided by r. So we'll cancel out one r here, we'll cancel out another r there, and we have g times mass of the Earth divided by r equals velocity squared. Now previously we wrote an expression where we said r, and I'll rewrite it here, r is equal to big R is equal to 3 times the radius of the Earth. And I'll just remind everyone that big R in this case, I'll do a different color, big R is the distance from center of Earth to center of satellite. Okay, so we will keep moving forward here, and we will plug in big R equals 3 times the radius of the Earth in for this down here. So we will say g times m divided by 3 times little r equals velocity squared. So we're almost there. We have everything that we need. We just need to solve for our velocity, and we get velocity is equal to g times m divided by 3r. And we square root that, and that is our answer. So let's go up above and see if there is an equivalent answer, if that's one of our options. And we see not these. This is a tempting answer, C, but our mass is canceled at some point, so this is not right, and we get answer D. So we see here that we talked about finding the distance from center to center, and that is what you use in your force of gravity equation. This big R here is center to center of mass, which is the same R that you use in your centripetal acceleration. So we know that we did a sum of forces on the satellite. The only force acting on the satellite was the force of gravity, and that equals mass times acceleration. And because it's traveling in circular motion, we know that the acceleration is equal to the velocity squared divided by the radius. And we solved for velocity to get this expression. So let me know if you have any questions in the comments below. And yeah, thanks for watching.